So let's take a look at number 15 now. And so on number 15, it says it has been found the probability density function for the wait to check out at a local grocery store is given by the following function for x bigger than or equal to 0, where x is the number of minutes spent waiting in line. And so in part A, we're going to calculate the probability that you wait 2 to 7 minutes in line. So in part A, all you need to do is compute the probability that 2 is less than or equal to x is less than or equal to 7. Right, and so the idea behind this is when I say probability, hopefully you think area, and then if you think area, you think integral. So you do the integral from 2 to 7 of this probability density function. So 0.1 e to the minus x over 10 dx. And we're going to use your calculator to do this. I really don't want to do it by hand, so I'll use my calculator. And so on my calculator, it says what? So I hit y equals and clear this out, and then I do 0.1, and then second ln, so e to the, I put negative negative x divided by 10 in parentheses. All right, so the idea is I'm going to graph this, and I'm going to graph it between 2 and 7, and then hit zoom fit. And I'm going to try to find the area underneath this curve here. All right, so I'm going to put these keys up here so you can kind of see what I'm doing. All right, so to find the area, I hit second trace. All right, so hit 2 to 7. It looks like this. I'll show some work. And so I hit second trace, and I go down to number 7, which is the integral of f of x dx. I hit enter. And it says lower limit, that was 2. Upper limit, which was 7. Hit enter. It's going to shade in this region. Right, and it's going to spit out my answer. So this is approximately, let's round this to, let's do, 2 decimal places maybe? So let's just do 2 decimal places. So 0.32. Right, so that's my answer. Or you could say, 32%. All right, and remember down here I hit integral of f of x dx to find this. And so I always like to tell, it's nice to know you guys know which buttons to push because I can give you some credit for that. Okay, so what does that mean? That means the probability that you wait between 2 and 7 minutes in line is about 32%. All right, so then in part B, it says, calculate the median wait time in line. All right, so notice it's not the mean, it's the median. So you look on your formula sheet, and the median is given by the integral from minus infinity to x tilde of the probability density function p of x dx equal to 1/2. All right, so now, after I write down the formula, what I want to do is plug in. So I have really the integral, and I don't have minus infinity because this starts at 0, so all the way to the left means start at 0, up to x tilde of my probability density function, 0.1 e to the minus x over 10 dx equal to 1/2. Right, and so now what I need to do is I need to solve this equation for x tilde. Now I could do it by hand, but it takes some work, and I can solve for x tilde. It's actually a good exercise in solving exponential equations. But I'm going to use my calculator, and the way that I use my calculator is I hit y equals, and I'm going to clear out the screen, and I have to put an integral in for y1, right? The idea is I'm going to graph the left, graph the right, and then I'll intersect to find where they cross. And so to put an integral in, I hit math, and I go up to finite integral, FNINT, right, which stands for basically definite integral. And then I have 0.1 second ln to the negative x divided by 10 in parentheses, comma, all right, I'm integrating with respect to x, so I put an x there, comma, then I put my limits of integration. So I'm starting at 0, so I start at 0, and I go up to x tilde. So I don't have an x tilde button, so I just hit x in parentheses. And then for y2, I put 1 divided by 2. For my window, so for my window now, I'm trying to figure out the median wait time. So what time do you think is kind of in the middle? Well, you can start at 0 and then go up to, well, I could really go up to infinity, but I don't think it's going to be that long. I'm going to go up to like, maybe I'll do 30 minutes, right? Because I don't think I'd wait in time in line longer than 30 minutes. And so then what I want to do is hit zoom fit. And this is going to take a couple minutes. What I'm going to do is I'm going to pause the video, and when it's done, I'll record again. So like magic, we're back, and mine has graphed. It actually took a couple minutes. And so what I want to do over here is I probably want to copy this down. So let's get some room here and copy it down. All right, so right here, maybe I'll copy down my graph. I went from 0 to 30, and it went up like this, and the half crosses like this. And I want to find where they cross, and so the idea is I want to find where they intersect. So to do that, I hit second trace to pull up the calculate menu, and then you know where to go. You go down to intersect. Hit enter, and then it's going to walk you through some questions, but you just can hit enter 3 times, right? So first curve, yes. Second curve, sure. Guess, that's close enough. And it's going to spit out the answer. So in this case, I'm going to find x tilde to be approximately, and we'll round this to 2 decimal places, so 6.93, and this is in minutes. So my median wait time would be 6.93 minutes. Right. Part C, so now in part C, they're asking me to calculate the mean wait time. Right, so on average, how long will I wait? So again, I pull out the formula. Right, from my formula sheet, mu is equal to the integral from minus infinity to infinity of x, p of x, dx. Right, and that's going to be equal to, I'll plug in some numbers. Now remember, I'm starting at 0, so I start at 0. And I do go to infinity, but I don't think I'm going to wait in line that long, but I do want to get a good approximation, so maybe I'll go to like 1,000 minutes, although I know I'd never wait in line 1,000 minutes. But if I go to 1,000, it should give me a really good estimate for my mean. And then I have x times, and I copy down what's there. So I have, for my probability density function, 0.1 e to the minus x over 10 dx. And so now I'm going to plug this into my calculator. All right, so into my calculator, I have y equals, and I'm going to clear all this stuff out because I don't need it anymore. And then for my y1, I'm going to just put x times 0.1 times second ln, and then I have negative x divided by 10 in parentheses. And for my window, I'm going to go from 0 to 1,000. I'll zoom fit it. It shouldn't take too long to do this. And so there it goes from 0 to 1,000. Looks like it almost goes straight down, right? It goes down and probably levels off. Not going below the x-axis, though, so let's get rid of, it looks like I drew it below the x-axis, so let's just crunch that off there. Okay. So now I want to find the area underneath here, because that's what this definite integral represents. So now I'm going to do the integral of f of x dx button. So second trace, go down to number 7. Lower limit was 0. Upper limit we went to 1,000. Hit enter. It's going to crunch it, and it's to tell us that this is actually equal to 10. All right, so this is 10 minutes. So the average wait time, the mean wait time, is 10 minutes, whereas the median is slightly less. All right, remember the median, which is up here, was what, 6.93 minutes? Okay. The next problem we want to look at is one involving identifying the local maxima, local minima, inflection points of the function, determining the end behavior and intervals on which it's increasing, decreasing, concave up, and concave down. And we want to use the same function to find the global maximum, global minimum values on for x less for 2 less than equal to x less than equal to 5. Okay. So let's do part A first. It's actually 2 problems. All right, let's take a look at part A. So to do part A, what you need to do is the first couple steps. So we want to do step 1. All right, and step 1 is to find the critical points of f. So remember, this is when f prime of x is equal to 0. So we find f prime of x. So what's f prime of x equal to? Well, we take the derivative, and we get 3x squared minus 12x plus a 9. All right. And we can set this equal to 0. So we set this equal to 0 then. And remember, we can actually factor out a 3 here. So let's factor out the 3, because then we can factor the quadratic. So if we factor out a 3, this becomes a 4x. This becomes a 3. And then the factorization becomes rather obvious. This is x minus 3 times x minus 1 equal to 0. So either this is 0, which means either x is equal to 3, or x is equal to 1. So I actually have 2 critical points. Okay. Then I want to do step 2, which is find the critical points not of f, but of f prime. Right, that'll give me possible inflection points. So on step 2, what I want to do is I want to find, now I want to find the critical points of f prime. So this is when f double prime of x is equal to 0. And so over here I find f double prime of x. It's equal to, well, the 2 comes down, I get a 6x. Sorry, I'm just looking at this. The 2 comes down, I get 6x minus 12. I set this equal to 0, so 6x minus 12 equal to 0. And I get 6x equal to 12, or x equal to 2. All right. These points here tell me where to look when I make my graph. So the final step is just make a graph, and from the graph I should be able to read off all the things that I care about. And so I take out my calculator, and let's just move this over here. And what I want to do is hit y equals, clear this out, and I want to graph my original function. So let's go back up and plug in my original function. So I have x raised to the 3, so x cubed minus 6 x raised to the 2, right, x squared, plus 9 times x, so 9x, plus a 2. And I'm going to make my window, and now my window, I'm going to set my minimum x value at the smallest number I found. So I found 1, 2, and 3. So the smallest one would be a little bit less than 1, so 0. Right, so you want to go a little bit to the left of it. So if the smallest one's 1, I'll do 0. Now the biggest one I found was 3, so I'll do a little bit more, so that's 4. And then I'll zoom fit it. I should get a nice looking picture, which I do. So down here on the graph, what I would do is I'd say, okay, I went from 0 to 4. And what did it do? It goes up, comes down, and then goes back up. Something like that. All right, and then this point here, all right, which you can pretty much guess, this is probably the input is 1, because you have 1 here, so you can trace it. Trace 1, enter, and you get out 6. And then this point here is probably an inflection point, right? This is a max, so maybe I'll write max there, and then I'll write I and F here for inflection. And that's probably 2 comma, so I can hit 2 and enter, and it'll tell me that's 4. All right, so when I plug 2 into my function, I get out 4. And then down here, this is obviously a min, and so this is probably 3 comma something, so 3 enter, and I get out 2. And that's all I need to answer basically all the questions I want. So now remember, what am I trying to find? I'm trying to find any local maximum, local minima, inflection points. So first, let's talk about local max. All right, well, this occurs at f of 1, which equals 6. Local min, well, this occurs at f of 3, which is equal to 2. Right, plug in 3, get out 2. And I do have an inflection point at what? 2, 4. Right, so there's those first 3 questions I answered. And now I want to figure out the end behavior. Okay, so I can look at the picture and figure that out. So end behavior. So remember, end behavior, what's that? The idea is what happens as the limit as x goes to, let's say, negative infinity all the way to the left of f of x. Well, the graph tells me it's going down, so it goes to minus infinity. Versus what happens on the other end, that's when x goes to positive infinity of f of x. So as I go all the way to the right, the function continuously is going up, so it goes to positive infinity. So that would be describing my end behavior. Where is a function increasing? Right, well, it's increasing from minus infinity all the way up to here to 1. Right, always the input describes this. Union, and then I decrease from here to here, then from 3, right, so from 3 to infinity. Right, so all the way out to the right. And I decrease in between, obviously. I'm decreasing from here to here, so from 1 to 3. Okay. Where am I concave up? Well, I'm concave up. Well, I'm concave down. I'm frowning, all the way till I get to the inflection point. And from this inflection point, then I'm always concave up. So I'm concave up from 2 to infinity, which then also means I'm concave down from minus infinity to 2. And that's obvious from the picture. And then I think I answered everything in part A. Yep. I gave the intervals increasing, decreasing, concave up, concave down. Okay, part B. So on part B, what does it say? If you look back at the question, it says find the exact global maximum, global minimum on 5. And so the way this works is you take out your calculator, right? All you really need to do is look at the graph. But you want to look at the graph between 2 and 5. So change your window, because all you care about are values between 2 and 5. And we'll zoom fit it. And so between 2 and 5, here's what it looks like. So here's 2, here's 5. It starts up here, comes down, and ends up there. Right? You can figure out these values, right? You just figure out where it starts by hitting trace. So it starts here at 2, up at 4. This we've already found. This is the point 3, 2. And then this height up here, right? This is the point 5, well, if you plug in 5, you get out 22. And we want to figure out where do we have a global maximum or global minimum. So global min, which is the lowest value between 2 and 5, which of course occurs at here at height 2. So we'd say global min f of 3 equal 2. And global max then at one of the endpoints, obviously, this endpoint here, which is f of 5, equal to 22. And so that answers part B, which again, find the exact global maximum, global minimum values when x is between 2 and 5. So on number 17, what we want to do is use the definition of the first and second derivative of f of x equal x squared minus 1. Oh, this should say use the first and second derivative of f of x equals, what are you given? No, this is messed up. This should say use the definition of the first and second derivative to find. Well, this is all messed up. Okay, so I fixed it here, and on your copies, hopefully it's fixed. It says use the definitions below to find the first and second derivative of f of x equal to x squared minus 1. You were given that, and so here are the definitions. Okay, so let's do this. So you're given f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And so the first step is just to do what it says, and what it says is write down the limit as h goes to 0, because we haven't evaluated the limit yet. And f of x plus h means wherever you see an x, you replace it with x plus h. So here I have x squared, so I'm going to replace that with an x plus h squared, right, minus 1. Right, so remember, a function's a rule. The rule is whatever's inside here, you square it and take away 1. So this is inside, so I square it and take away 1. And then minus f of x, so minus my f of x, which is just x squared minus 1. Notice I put parentheses around it because I'm taking off the whole quantity, all divided by h. And so this is equal to, again, I haven't evaluated the limit, so I have to keep the limit on there. The limit as h goes to 0. I'll square this out. So when you square it out, you get x squared plus the middle term, 2xh, plus h squared, and you have minus 1. Distribute the minus sign through here, so you have minus x squared, and a minus is a plus 1. Right, all divided by h. So you're going to get a lot of things canceling here. This cancels, and this cancels, this cancels, and that cancels. And so this is equal to the limit as h goes to 0 of 2xh plus h squared, all divided by h. Right. There's still more algebra to be done here. You can tell this because if you try to plug in h equals 0, you get 0 on top and 0 on bottom, and that's one of our indeterminate forms. And so what you need to do is factor out an h at the top. So this is the limit as h goes to 0, and pull out of h on the top. So I'll pull out this h, so I get h times 2x plus h here, all divided by h. And now these cancel, and so this is where this indeterminate form goes away, because the h's will cancel, so you won't get 0 on the top or bottom anymore. And I just have 2x plus h. Now I plug in h equals 0, so I get 2x plus 0. Notice I dropped off the limit because I plugged in 0 for h, and so that's just equal to 2x. And that's exactly what you would expect it to be. If you take the derivative of this using the rules, you'll obviously get 2x. F double prime of x is equal to, again, we just copy down the definition, the limit as h goes to 0. Instead of f of x plus h, you have f prime of x plus h minus f of x divided by h. And so this is equal to, do what it says, so we write down the limit as h goes to 0. And where I have f prime of x, which is 2x, I plug in an x plus h. So I get 2 times x plus h, because f prime of x says whatever inside here, whatever inside, multiply it by 2. So I multiply whatever's inside here by 2, and I take off f prime of x, which was 2x, all divided by h. This is equal to, again, I haven't evaluated the limit, so the limit stays. The limit as h goes to 0. And then I have 2x, let's multiply through by the 2, plus 2h minus the 2x over h. The reason I'm doing this is because then the 2x's will cancel. So now I have the limit as h goes to 0 of 2h over h, right? And this is where the h's cancel. And so I get the limit as h goes to 0 of 2. So now I plug in h equals 0. There's no place to plug it in, so I just get back the number 2. And that's my answer. All right, the next problem, number 18, this is an optimization problem. So it says a landscape architect plans to enclose 3,000 square foot rectangular region in a botanical garden, use shrubs costing $15 on 3 sides, and fencing costing $10 along the 4th side, and we want to find the minimal cost. So for my picture, I draw a rectangular region. I know the area is equal to 3,000 feet squared. I know on 3 sides I'm going to do shrubs, so let's just do some shrubs here. So these are my shrubs. All right, my shrubs, they're what? So shrubs, they're $15 per foot. And then on my 4th side, right, I'm going to put a fence, and I know my fence is $10 per foot. And I want to find the min cost. Very important, because this is going to tell me my equation. It's not an area equation or a perimeter equation. It's a cost equation, because that's what I'm minimizing. And so the cost, I have to figure out, well, how much is this going to cost? Well, I'll call this side x, this side y, this side x, this side y. And so if I have x feet and it's $15 per foot, this guide's going to cost me 15x, plus then I have 15y for that side. This side's going to be, again, another 15x. And then the final side over here is not going to be 15y, because it's not $15 per foot. It's $10 per foot, so it'll be 10y. And so my cost, 15x plus 15x, is a 30x, right, plus 15 and 10, so 25y. And so what I'd like to do is take the derivative of this and set it equal to 0 and solve for x. But I can't do that because I don't have just x here. I actually have x and y. So I have to get rid of y somehow, and that's where this 3,000 comes in. So I know the area is 3,000, which is x times y. And so I can solve this for y. Y is equal to 3,000. Right? And to move over x, since I'm multiplying, I just divide. And so c is equal to 30x plus 25 times 3,000 over x. I can figure this out on my calculator, right? So I have 30x, and I can do 25 times 3,000, which turns out to be 75,000, right, over x. Now I have a function of one variable, so now I can take the derivative. So now I'm going to solve. So c prime of x is equal to, right, derivative of 30x is 30, and now I might want to rewrite this as a power of x, so I can take the derivative, so x to the minus 1. And so the minus 1 comes down, so I get minus 75,000 x to the minus 2, right, which is the same thing as 30 minus 75,000 over x squared. All right, so now I set this equal to 0, so 30 minus 75,000 over x squared equal to 0. Remember, we're setting it equal to 0 because when the derivative is 0, you get maximums or minimums, right? Because you either have peaks or valleys. And so I set the derivative equal to 0, and I solve for x. So to solve this for x, let's just move over the 75,000 divided by x squared. So you add this to both sides. You multiply both sides by x squared, so you get 30 x squared equals 75,000. Divide both sides by 30, and you're going to get x squared, so your calculator will tell you 75,000 divided by 30 is 2,500. And then take the square root of both sides. The square root of 2,500 turns out to be 50, and that's 50 feet. Okay, but you don't want 50 feet, you want the minimal cost. So to find the minimal cost, you plug this into your original function. So c of 50 is equal to, right, so you have 30 times 50 plus 75,000 divided by 50. And if you put this into your calculator, you're going to get out 3,000. Now this is cost stuff, so $3,000, and that's my answer. Okay. You can test this. All right, so to test this, the way you do it is you take your calculator and go to y equals, and we'll clear out all this stuff here. And you plug in the formula you found for c in terms of x. So you have 30x plus 75,000 divided by x, so plus 75,000 divided by x. You make your window, and for your window, we're going to go from 0 to, we found x to be 50, so let's do like 200. Let's see if that's big enough. So zoom, zoom fit. And we want to see it go down and come up. That's good enough, right? So we went from 0 to 200. And you see how the cost is driven down, but then eventually goes up. We want to find this minimum, so you can do that by hitting second trace. And you see you have a minimum button right here. So go down to minimum and hit enter. And it's going to walk you through it. Left bound, well, 0 is on the left, right? You can see 0 is on the left. And right bound, well, 200 is definitely on the right. Give it a guess, just hit enter, and it'll jump right to the minimum, 50, comma 3,000. So as long as your formula is right here, everything else that followed, the analysis that followed, is correct because you got the same answer. Okay, and then now on number 19, we have a Lagrange multiplier problem. Now remember, you'll be allowed to use that formula sheet, and on that formula sheet, it tells you that you need to first, find these partials with respect to f. So, f sub x. And the idea is you hold all the y stuff constant. So derivative of x squared is just 2x plus, and then 4xy. 4y is a constant. So basically you have 4y, a constant, times x. So you just get back the constant, 4y. F sub y now x is a constant. So this is 0, right? Derivative of constant 0. And then you just get back 4x, right? A constant times y, the derivative is just a constant. Over here, this is our g. So g sub x is just equal to 1 plus 0. And g sub y, now x is constant, so that's a 0 and that's a 1. So you just get back 1 again. You make these Lagrange equations. Right? So you have f sub x, which is 2x plus 4y, equal to lambda times g sub x, so just lambda, because lambda times 1 is lambda. And you have 4x, right, f sub y equal to lambda times g sub y, which again is just lambda. And then down here you have x plus y is equal to 100. And you want to solve this system of equations. There are lots of ways to do this. Maybe the simplest way to do this is, since these two things are equal to the same thing, let's combine them. So this tells us that we can say 2x plus 4y is also equal to 4x. And so then we can move over the 2x, right? So you get 4y equal to 2x if you subtract 2x from both sides. Then let's divide both sides by 2, right? So then you get 2y equals x. Right, so now I know x is equal to 2y, so I can come back over here and plug in for x. So I get 2y plus y is equal to 100. So I know 3y is equal to 100. And so this tells me that y is equal to 100 divided by 3. Right, so that's my y. So that's something. And if y is 100 divided by 3, I can tell you what x is, because I know x is 2 times y. So it's 2 times 100 divided by 3. So that's 200 over 3. And the question here, it's saying, find the maximum or minimum value subject to this constraint. And so what I found is the x and y that give me the maximum or minimum. So what I need to do now is find it. So that's f of 100 over 3, comma, 200 over 3. And I plug this back into the original function. Right, so up here I look at it, so this is equal to 100 over 3 quantity squared plus 4 times 100 over 3 times 200 over 3. Oops, I messed this up, right? I got these backwards. Oh, let's erase that. So I just realized I put the x in the wrong spot. So restart. So this should be f of 200 over 3, comma, 100 over 3, which equals, now I'll get it right, so 200 over 3 quantity squared, right, because it's x squared, plus 4 times x, so 4 times 200 over 3, times y, which is 100 over 3. And I'll just use my calculator to do this. And so if I plug this into my calculator, let's see what I get. So this is going to be approximately what? So let's move this over. Clear this. All right, so on here I have left parenthesis 200 divided by 3 raised to the 2 plus 4 times 200 divided by 3 times 100 divided by 3. And that's equal to about 13,333.33. And is this a minimum or a maximum? Well, to decide this, I go back up and I look at my constraint. Okay, so what is my constraint? My constraint is x plus y is equal to 100. So let's let x be 0 and y be 100. All right, so this, let's look at f of 0, comma 100. This satisfies the constraint. And then you plug this in. This is 0 squared plus 4 times 0 times 100, which is a 0. And so this is a number that's smaller, so this must be a maximum. Right, so f of 203 to 3,000, which is a maximum. And then for a minimum, right, there is no minimum. Otherwise, we would have found another point. There is no minimum. So no minimum, and then this is the maximum. We did that by testing, finding a point and testing it and seeing, oh, this is smaller, so this must be the maximum, and there must not be a minimum given this constraint. All right. So the next one, number 20, what do we need to do? Well, it says use the fundamental theorem of calculus to evaluate the following definite integrals. You must do these by hand, but you could use your calculator to check the answer. All right, so let's just do part A first. All right, so for part A, this is equal to, well, I can integrate this. This is relatively easy. The antiderivative of 2x is x squared, right, minus 5x from 2 to 7. And then the idea is first plug in 7, so I get 49, minus, now plug in 7. 5 times 7 is 35. Minus, now plug in 2, so I get 2 squared, which is 4, minus 10. And so what is this equal to? Well, this is equal to 49 minus 49 minus 35, which is 14. Minus 4 minus 10, well, that's a negative 6. And so this is equal to 14 plus 6, which equals 20. All right, so I get 20 here. On the next one, on this side, all right, to integrate this, I'm going to have to do a substitution. So let's let u be equal to x squared, which means du will equal 2x dx. All right, and I need to change my limits of integration. So u of 3 is equal to 3 squared, which is 9. And u of 0 is still equal to 0 squared, which is still 0. All right, so this is going to be equal to the integral from 0 to 9. All right, here's my u. So there's no problem there, so that's going to be e to the u. But this x dx is a slight problem because I don't have x dx, I have 2x dx, but that's okay because I can divide both sides by 2 and then get du over 2 equal to x dx. So this is actually then a 5, and then x dx is my du over 2. And so this is equal to, let's pull out the 5 on top and the 2 on bottom, so 5 halves, the integral from 0 to 9 of e to the u du, which is relatively easy to integrate. It's just 5 halves, integral of e to the u is e to u from 0 to 9. And then we can just plug in, so we get 5 halves e to the 9th minus 5 halves e to the 0, which is the same as, if you want, you can pull out the 5 halves, and you get e to the 9th minus 1 for your answer. On number 21, it says the size of an exponentially growing bacteria colony triples in 2 hours. How long will it take for the number of bacteria to quadruple? All right, so remember this is using the exponential function. So the idea is write down the formula, right? So it's p equals p naught e to the kt, and use this formula to figure out the time will it take for the bacteria to triple. So we use the first sentence. It grows exponentially. That says I use the exponential function. And it triples in 2 hours. Okay, so that means if I plug in 2, so let's plug in 2 for t, that it's going to triple. And so that means I get 3 times the original amount. The original amount is p naught, so I get 3 p naught. Right, what's nice about this is if you divide both sides by p naught, they're going to cancel, and so you just get e to the k times 2 equals 3. And you want to solve this for k, so to solve for k, you have to bring it down, so you ln both sides, and when you ln both sides, you get k times 2, ln of e equals ln of 3, and ln of e is 1, so you can just drop it off, and so you get k, right, k times 2 to equal ln of 3, and so k equals ln of 3 over 2. And so now what you know is something a little bit more. So what you know now is that p is equal to p naught e to the ln of 3 over 2, right, with the t up there. And now you want to figure out how long it takes for the number of bacteria to quadruple. So the idea here is you write down the formula, and you pretend now that t is the time it takes to quadruple. And so to quadruple means you have not 1 p naught, but 4 p naughts. Right, again, p naughts will cancel if you divide both sides out, and you get e to the ln of 3 over 2, t equal to 4. To bring down the exponent, you ln both sides. So we'll ln both sides, and we'll get ln of 3 divided by 2 times t ln of e equals ln of 4. ln of e is 1. And so now we can just solve for t. So t is equal to, right, to move over divide by 2, you multiply by 2. So you get 2 ln of 4. And then to move over the ln of 3, you divide by ln of 3. So this is the exact answer. Right, if you want to round this, right, you can put in your calculator and figure out what it is to 1 decimal place if you like. So, but this is the actual answer. But you want to see the number, you'd say, okay, 2 ln of 4 in parentheses divided by ln of 3 in parentheses, and you get out about 2.5 hours. So it takes about 2.5 hours for the colony to quadruple. All right, so we're almost done here. Let's take a look at the last couple problems. So 22, it says the bulb life of a light bulb follows a normal distribution with an average bulb life of 300 days and a standard deviation of 50 days. We want to determine the formula for the density function and determine the probability that a light bulb will last more than a year. Okay, so what we need to do is first determine the probability density function. And since this is said to be normally distributed, we know that the formula for the probability density function of a normal distribution is p of x equals 1 over, and we have sigma square root of 2 pi, e to the minus, and we have x minus mu, quantity squared, over 2 sigma squared. Let's make that square better. So squared. And so we can find the formula because we know the mean is 300 and the standard deviation is 50. So the probability density function p of x is equal to 1 over 50 square root of 2 pi, e to the minus, you have x minus 300 squared, all divided by 2 times 50 squared. And you can rewrite this then as 1 over 50. This stays the same. And e to the minus, and you have still x minus 300 quantity squared. The only thing that can be simplified is this bottom. 50 squared is 2,500 times 2 is 5,000. So there's the probability density function. So on the second part, what we want to do is we want to determine the probability that a light bulb will last more than 1 year. So what we want to do here is figure out the probability that x is bigger than or equal to 365. And so that would be equal to the integral from 365 up to what? Well, more than 1 year would be like to infinity, as long as you want. And then we have the probability density function, 1 over 50 square root of 2 pi, e to the minus, and here we have x minus our mu, so 300 squared, over our 5,000 like we had before, and then all dx. And this is all up in the exponent. And so I don't want to do this by hand. I'm going to use my calculator to do this. So hit y equals, and then put in the integrand. So put this thing in there. So 1 divided by, and then left parenthesis, 50 second square root of 2 second pi, in parenthesis, second ln to get the e to the button there. And then I have a negative, left parenthesis, x minus 300. Right parenthesis, raised to the 2, divided by 5,000. All right, in parenthesis. My window is going to go from 365 up to a really large number. So let's go up to like, let's do 10,000 days. All right, that's pretty big. And so then do zoom fit. All right, so if you do 10,000 days, you get a graph, and it looks like it's basically going almost straight down. So on my graph right here, it looks like I'm going from, let's see, 0 to like 10,000, and it's going basically straight down there. And I want to find this area, and so to find the area, I hit second trace and go to the integral of f of x dx. And so I hit number 7. And the lower limit was 365. And the upper limit, we're going to make 10,000. And then hit enter. And I'll spit the answer out there at the bottom. And so this is approximately 0. Let's do like 9, 0.09. Let's just run 2 decimal places, 3 decimal places, so 0.097. Or you could say 9.7%. So how many of the light bulbs will last more than a year? Only just about 9.7% of them. All right, the last two questions involve limits. And so here the idea is you look at the graph over here and you decide what the limit of 3 is. Now remember, a limit is sort of like your best guess for the function at the point. And the way it works, you look at the left and you see that you have a guess. You look at the right and you see you have a guess. If those guesses are the same, the limit exists, and it is that guess. If the guesses are different, then the limit does not exist. So like as you go to 3, here 3 is right here, you see as you come in from the left, you hit 2. As you come in from the right, you hit 2. Oh, so the limit must be 2. So the limit as x goes to 3 is equal to 2. Again, you can kind of see this, right? So it's like as I approach 3 from the left, I go to 2, and from the right, I go to 2. All right, now this one, right, what does this say? This says the limit as x goes to 1 from the negative side, so from the left-hand side of f of x. So here's 1 right here. As I come in from the left, right, you see I approach the height of 2. So this is equal to 2. But as I come in from the right, so this little plus sign means the right, so I come up here, right, you see I hit a height of 3. So that's equal to 3. Because these two values are not equal, the limit as x goes to 1 f of x, we say this is, right, equals does not exist, right? So for does not exist, we're going to D and E. Now this is different though when we go to 5. So here's 5 over here. So let's see 5. So 5 is right here. So as we go to 5, we see from the left we hit 4, and from the right we hit 4. And since those values agree, we conclude that the limit as x goes to 5 of the function is actually 4. And so that's how we do limits from a graph. And then from a formula, right, how do we do these? Well, the simplest way is first we just try to plug in the point. So plug in -3. So it says this is -3 squared minus 2 times -3 plus 1, which is 9. And then this is -2 times -3, so it's plus 6, right, plus 1, which is 16. That's a fine number, so the limit, your best guess, as you get closer and closer to -3 is actually 16. All right, this one down here, the same idea applies. You try to plug in 2, so you get 2 squared minus 2 minus 2. And on the bottom, you have 2 squared minus 5 times 2, so minus 10 plus 6. And you'll see on top, you're going to get 0. On the bottom, you're going to get 0. And so this is what we call indeterminate form. Which means you cannot determine the limit as given. So you need to do some more work here. Right? So the idea is if you take the limit as x goes to 2, what you can do is you can actually factor the top. So the top actually factors x minus 2 times x plus 1. Divided by, and the bottom also factors, this is x minus 2 times x minus 3. And you can see here, then you can cancel off these x minus 2's, and that's where the indeterminate form goes away. Because if you plug in 2 for x, you'll see that's 0 and that's 0. So now you get the limit as x goes to 2 of x plus 1 over x minus 3. Now plug in 2, and so you get 2 plus 1, which is 3. And on the bottom, you get 2 minus 3, which is a -1. And you get out -3. So -3 is the answer for that limit. All right, and the idea is as x gets closer and closer to 2, this thing will get closer and closer to -3. And you can even plug in points, like plug in 2.0001 in for x. And you'll see you get out a number really close to -3.